Good morning students. Welcome to another video of cryptography. In this video we will be sharing about the concept cipher block modes of operation. As we all know, the blocks of information can be processed in various techniques. One is the stream cipher, the other is the block cipher. In block ciphers, the processing will be done blockwise. How many bits a block is being saying, like let me say a block is 4 bits, then each 4 bit will be processed at a time. But in the case of stream cipher, the processing is done bit by bit. So as long as the PT is like the plain text is, the ciphertext will be also the same. So moving on, the ways or the modes of operation in which a cipher block is being processed, we are going to deal with that topic today. See, as we know, in symmetric block cipher, it produces each block of plain text for each ciphertext. That is, exactly for one block, another block will be produced. In the common algorithms we use for block ciphers like DES and DDS, the block size B will be 64 bits. And for AES or Advanced Encryption Standard Technique, the bit size or the block size is the double, that is 128 bits. When the plain text is really large, we are supposed to split it into multiple parts and then process it, and at last we combine it to get the plain text as it is. So this processing can be done in various techniques. Now let's discuss the 4 main modes of operation dealing with it. The first one is ECB. ECB is electronic code book mode. Second one, the CBC, that is cipher block chaining mode. Here a chaining process will be done. Third one is cipher feedback mode. So some sort of feedback is taken from each block towards the next succeeding ones. And the fourth one is counter mode. Okay, so I've been saying about the 4 modes of operation. One is the ECB, CBC, CFB and counter mode. Let's see ECB in detail. ECB is electronic code book mode. This is actually the simplest way of cipher block mode of operation, you can say. Here what is happening is each block of plain text is handled B bits each, and using the same key we encrypt it to get the ciphertext. I hope everyone is clear about the concept plain text and ciphertext. In short, plain text is the original message which we send from the sender to the receiver, and the scrambled message which makes or which tightens the security, that is called as the ciphertext. So here I have been saying this is the simplest technique in which each plain text is handled B bits at a time, and each block of plain text is encrypted using the same key. I hope what do you mean by same key? Same key is nothing but symmetric encryption, which we have been dealing all these classes. Okay, so as the term suggests, electronic code book. What is a code book? What does a book contain? Here also a code book is nothing but for a particular key, for a particular plain text, there will be a unique ciphertext. And there is a small drawback in this. You can imagine a gigantic code book which contains for a particular plain text, because as many times the same code of plain text is repeating, the same unique ciphertext will also be repeating. So multiple times a repetition is occurring in a plain text. For example, I am using the term this is my video, and this sentence is being repeating in my sentence 4 to 5 times. The same code will be generated for the same key 4 to 5 times, and all this data will be stored in this code book, and that's why we call it as in effect it's giving a code book look, and that's why we say, so that's a big drawback, because the cryptanalyst who is trying to exploit or who is trying to crack the information, for him it is actually easy, because the same information is being repeating multiple times, and so it's easy for him to crack, okay, this is the technique which he's using, or this is the type of code which he's trying to use. So it's easy for him to exploit it. So that is one big drawback of this electronic code book mechanism or mode. Okay, so we have already learned the what manipulations can be done on the plain text. For example, substitution or some sort of rearrangement. All such happenings can be done by the cryptanalyst in this case, because multiple times or repetition is a big drawback. So to overcome the security deficiency of EBC or electronic code book, we are using the second mode of operation, that is CBC, that is cipher block chain. Let's see what it is. So now we know about electronic code book mode, the first mode of operation in which the cipher blocks are being processed. What was the drawback there? For multiple times a repetition occurs. That is the drawback. That is, for each key and for the same plain text, a unique CT or ciphertext is being generated. So as many times the plain text is repeating, as many ciphertext will be also repeating. That is the major drawback of electronic code book. To overcome this deficiency, we are moving on to a new technique in which even if the plain text are repeating multiple times, the ciphertext won't repeat. It won't be exposed because each block it is being carried over with some XOR operation. So no matter if the plain text is repeating or not. Okay, now let's see how it works. So this is CBC or cipher block chaining mode. So as the term indicates, there is some sort of chaining that is occurring in this. So some sort of chaining for the processing of plain text is being used here. Let's see, first let's see some common concepts dealing with it. You have an IV here. IV is nothing but initialization vector. It can be any value as per, like commonly it is like as per the number of bits of the plain text itself, so that it's easy to calculate. So for example, my plain text is 4 bits. I take any random number or random value, you can call it as initialization vector, and I make sure that random value is also of 4 bits so that the operation can be done smoothly. Clear? For the first block, it will be the IV. Okay, from the next block onwards, it will be the preceding ciphertext. Let's see how it happens. So encryption. This is the encryption part till here, and then you have the decryption. Let's see what's happening in the encryption technique. You have the plain text with you. Actually, this plain text is the first unit of your plain text. I have a large plain text, and for example, I'm dividing it into 4 parts. So this is the first unit of my plain text that will be indicated as P1. So P1, it is XORed with the so-called initialization vector, and the result you obtain is given as the input to the encryption algorithm. Okay, some sort of algorithm is being used, right? So that is the input to encryption algorithm. While using the algorithm, you have a key K, and as we have been saying all this time, this is symmetric encryption. So the same key is used for all the blocks. Okay, no change in the key and all. The same key is being used. So let it be like K itself. No more suffix and prefix is needed there. So for the algorithm, key K is being used, and the result will be the cipher text. Okay, corresponding to the plain text unit. So for P1 unit, C1 unit is being generated right now. What happens in the second block? Second block, again you have the second unit of plain text, that is the P2, and what is to be XORed with it is the preceding cipher text unit C1. So now you have the C1 with us, right? That C1 is XORed with the P2 which we have in hand. Both are XORed, which is again given as the input to the encryption algorithm where the key K is being used, and finally you get the new cipher text unit which is corresponding to the second unit of plain text P2. So for P2 we have obtained C2, and now the process is actually repeating again till how many blocks you have divided or how many units you have divided or the total number of units of your plain text. The process is being repeating. So in effect it is giving a chaining effect. Okay, in what do you mean by chaining? One after the other, and the one is actually linked with the other. The one becomes one output of one block becomes the input of the other block. So that is called chaining block. Clear? So one thing to make sure is that this initialization vector is a value, actually it is known to both the sender and the receiver, because in decryption also for the first block you need this initialization vector and it should not be changed. Okay, the same initialization vector, the same key is being used for encryption and decryption. just the process reverses. Okay, let's see. So what happens in the first block, P1, it's XORed with the initialization vector. The result is given as the input to encryption algorithm, where the key is being used to encrypt it. Some secret key must be used, right? And you produce the ciphertext unit C1. Now this C1 is then XORed with the second unit P2 to get the result, which is given as the input to the second encryption algorithm to produce the second ciphertext unit C2. And this repeats till, let it be like n blocks or n units. So till the Pn, this will happen. So what is being XORed with Pn? The preceding cipher, that is Cn minus 1. For P2 it was C1. So Cn minus 1, 2 minus 1, that's C1, right? So for Pn it will be, of course, Cn minus 1. That is XORed with Pn to get the input which is given to the encryption algorithm, and finally you get the cipher text for that particular unit, Cn. So while processing, what is happening? You have been breaking, or you have split the plain text into various units. So that much units of ciphertext is also obtained right now. And finally, ultimately, we combine these ciphertext, and then we can say the same process is being repeated in the decryption also. And when you combine it, you will get the plain text as it is. Okay. So this is regarding the encryption. Now let's see what's happening in the decryption. In the first block, as we have already said, what is happening in decryption? First, let's see what is happening. The reverse of encryption. So the plain text is being divided, P1, P2 up to Pn. Same way I got C1, C2 up to Cn, right? Now what is with me right now at the receiver end? I have C1, C2 up to Cn. Now it's my duty to convert it into corresponding plain text unit P1, P2, etc. up to Pn using the decryption algorithm. The same key K will be used for both the process. Let's see what's happening. C1, which is actually the first cipher text unit corresponding to P1. That's the only thing which I have right now. That enters the decryption algorithm. Okay, this algorithm is using some sort of secret key K, which is the same key. That result after decryption is then XORed with the so-called initialization vector, and finally you produce the plain text 1. Okay, I hope you have got the difference between encryption and decryption, because what is happening in encryption, you have the plain text, you XOR it with the initialization vector or the preceding cipher to get the input that is given to the encryption algorithm, and then you get the cipher concerned with it, or the corresponding cipher. In decryption, you have the cipher in hand. That cipher directly enters the decryption algorithm, where the secret key K is being used. That result is then XORed with the initialization vector to produce the corresponding plain text unit P1. I hope it's clear. Now, moving on to the second block, what is happening? C2. You have C2 in hand, right? The second unit, C2, is there with you. It directly enters the decryption algorithm where the key K is being used. The result is being obtained. It must be XORed with something, right? That something is nothing but the preceding ciphertext. What has happened right here is again happening in decryption also. Okay? Just the sequence have been a little bit modified, that's all. So C1 is being XORed with this decryption algorithm output to produce the corresponding plain text P2. And this process repeats till n units of your ciphertext, so that the n units of plain text is also generated. This continues till a Cn, and Cn directly enters the decryption algorithm, which is then XORed with the preceding ciphertext. It's Cn, so it's like Cn minus 1. It's XORed with Cn minus 1 to get the corresponding plain text unit Pn. Clear? So this is the encryption technique, and this is the decryption technique. So regarding CBC or the cipher block chaining, main things you have to keep in mind is that the same key is being used. Okay, the same key. It's because it's symmetric encryption. So the same key is being used for all the process for encryption and decryption. Second thing is that initialization vector is being used. In first case, that is for encryption, this initialization vector is one of the inputs that is being XORed with the plain text that enters the encryption algorithm. And case of decryption, where is this initialization vector? The output of the decryption is XORed with initialization vector to produce the plain text. So that is the significance of initialization vector, and make sure that happens only in the first unit of your cipher or plain text. From the second unit onwards, the preceding cipher text will be replacing its position. Clear? Yes. So in effect, we are giving a chained look for the processing technique or processing of sequence of plain text. You're giving a chained look. See, one is being chained with the other, so a chained look is given. And we have already dealt in electronic code book. The main deficiency or the main drawback is that multiple times repetition is occurring for the same plain text. That much times the CT is being produced, and this is overcome here. How? Because the input to every block has no fixed relation with the plain text block. For each block, the input is differing. Even though you are using the plain text, the same plain text, it is being XORed again and again. So some manipulation is occurring, and that makes sure repeating patterns are not exposed. Clear? Yes. Let's see main two equations dealing with this. What is happening in we have already written such equations. In encryption, what is happening? The function can be written as E of k x, where k is the key and x is the plain text x. We know all that. So let's see. This is for the encryption equation. The cipher is the output, so Cj, let it be Cj, is equal to encryption function of key k, and what is being the other input? XOR, right? So that XOR can be like preceding cipher XOR the current plain text. That is the input. Along with the key, using the encryption algorithm, you get the cipher unit Cj. Clear? So that is regarding encryption. Now let's see to the decryption. Even though it seems or looks like some complicated, actually it's very easy. What is happening in decryption? The exact reverse of encryption. So let it be like D of decryption of key k comma Cj. Okay, that is a cipher. You have the cipher in hand, and you're supposed to get the plain text on the other hand, right, or the right hand side. So let's see. Key k comma Cj is equal to D of the same thing, key k, and what will be replaced with Cj? The same equation. Okay, you have written in encryption Cj is equal to this much, and I have written as it is here. I've just replaced it. Clear? Now let's write. You can again rewrite it. How? D of k Cj is actually what? The preceding cipher XOR the plain text. The same what we did here. And if you are trying to make the equation much more simplified, you can XOR Cj minus 1 on both sides. Okay, so Cj minus 1 is being XORed with D of k Cj on this left hand side, and also I'm doing the same on the right hand side, so that there is no change in the equation. My aim is just to make the equation simplified, so I'm doing at the same process on the right. So Cj minus 1 is again XORed with the right hand side also. In XOR, I hope you know what's basic functioning of XOR. So Cj minus 1 XOR Cj minus 1 will give nothing else but 1. So 1 XOR Pj is nothing but the plain text Pj itself. So that's our motive. What is supposed to get in the right hand side? The plain text as it is, right? For the encryption process, you get the cipher, and for decryption process, using the cipher, you try to generate the plain text. That's it. Our next cipher block mode of operation is cipher feedback mode. So this mode of operation can be used to convert the block ciphers to stream cipher. As we know, actually stream ciphers can be used in real time, so it's more comfortable. And one important and desirable property of stream cipher is that the length of ciphertext will be as that of the plain text. That is, if the plain text is 8 bits, the cipher will also be 8 bits. If an 8-bit character is being transmitted, each bit must be processed using 8 bits only. If an additional bit is being used, the transmission capacity will be wasted. Okay, so here we are talking about S bits. S bits is nothing but just to indicate we are taking exactly S bits out of how many bits it will be. The block size, let it be small b as said before. So out of this b bits we are taking especially this S bits. So we are selecting only the S bits for encryption and decryption. Clear? Now let's see what's happening in cipher feedback mode. This is the encryption process. Here we have to understand all these time or all these modes of operation we have been using plain text as the input, right? Here the input is actually a shift register. Initially it will be some initialization vector as said before, and here also I have to say one thing, the initialization vector is also S bits in number. Okay, so how much is the plain text, that much will be the number of bits for the initialization vector for the first block. From the preceding onwards or the next from the succeeding blocks onwards, it will be the preceding value. Okay, now let's see. In encryption, for the first block, what is happening is the input will be initialization vector IV. Okay, it will be some sort of S bits only. So let it be like the block size is 64, but out of that I am taking only 20 bits. So S bits will be 20. The remaining will be discarded. 64 minus 20 will be discarded. Let's see. So initialization vector, it directly enters the encryption algorithm. Okay. Now out of this result, after entering the encryption algorithm, you get a result. You get some output, right? Out of this output, so from the beginning I am saying we are taking only S bits. So in case there are more than S bits, we are supposed to discard it at this point of time, and that's why you have been specifically writing this process in encryption. Let's see. IV, you have the input. That initialization vector is directly entered into the encryption algorithm, which uses some secret key K. So here also the same key is being used because it's symmetric encryption. The result, out of the result, you select the S bits and you discard the B minus S bits. What is B? The block size B. S is the selected bits, so S. So select S bits on the left hand side. Make sure you write it on the left hand side because that S bits is actually the MSB. Hope everyone knows what is LSB and MSB. When I write, when I write a digit like 1, 0, and 1, 1, this is the LSB, least significant bit, and this is the most significant bit. So the leftmost bit is actually the most significant, and the rightmost is actually the LSB. So let me repeat. Here you have been selecting the S bits and you have been discarding the B minus S bits. The selected S bits makes the MSB part of the plain text. Now how means? Now this S bits is being XORed with the plain text, which is again S bits. Okay, to get the corresponding cipher text unit C1, which is again S bits. That is the peculiarity of the term S bits, because we are exactly specifying or we are taking into consideration only the S bits out of the total block size bits B. Out of total B, whatever it is, we are considering only S bits. And make sure after the process of encryption, the first block of process, it becomes the MSB. Okay. Now I'll repeat once again. You have the initialization vector in the first block, because you don't have any other block or process at the before stage or the preceding stage. So the initial stage or the first block, you have initialization vector. This initialization vector directly enters the encryption algorithm, which uses some key like K. The result, out of the result, you select the S bits, which makes the MSB, and you discard the B minus S bits. Out of the selected S bits, that will be XORed with the P1, which is again the first unit of plain text. We have been studying all that, because if the plain text is large, we are supposed to break it into different or multiple units. So let P1 be the first unit. So while breaking also, make sure that P1 is of S bits. Then only we can do XOR. Then only we can do bitwise XOR. Now this selected S bits is XORed with the P1 to get the C1, which is again S bits. Now what happens in the second block? This C1 is actually now the input to the shift register. So what is happening in the shift register means the data is being shifted left, towards the left. Okay, so when it shifts towards the left, what happens is that the MSB S bits right now becomes the LSB. Clear? I'll repeat. Here the S bits or C1 is actually the MSB side right now. Now while it enters the shift register, it is shifted towards the left, so that this C1 constitutes the LSB part. So the C1 part is actually this S bits. This is the remaining B minus S bits, whatever we have shifted, right? Now this again enters the encryption process or algorithm, which uses the secret key, and out of the result again we are going to do the same process. You select the S bits and you discard the B minus S bits. The selected S bits become the LSB, and that is then XORed with the second unit of plain text P2, which is again S bits, to make sure you generate a C2, which is again a S bit. Clear? Yes. Now this process is being repeated how many times? How many units you have divided the plain text, that much times this process is gonna repeat. So let it be like CX, it repeats X times. So the last, let it be like it enters the shift register. So the preceding ciphertext is now shifted left, towards the left, to make sure that cipher constitutes the LSB S bits. Clear? And that enters the encryption algorithm. Out of the result, you select the S bits, you discard the B minus S bits. That selected S bits is XORed with the last unit of your plain text, let it be PX, which is again S bits, to produce the CX cipher unit of the corresponding plain text unit. And make sure that is also ciphertext unit which is having S bits. Clear? So let me just conclude what have I said. The first point I have written is, let SS of X, you have been seeing SS of X is nothing but is the MSB S bits of the plain text X. So you have the plain text S and the MSB S bits. If I'm saying the standard S bit is 8 bits, okay, let's assume it's in our text and your prescribed text, you have been seeing the standard sizes for a small s is 8 bits. Okay, so the MSB part, MSB 8 bits, that value will be SS of X. Clear? In encryption, what is the input? Input is the B bit shift register. That's the case of from the second block. In the first block or initially, the input is the initialization vector. Exactly. Now the second point, the MSB S bits are of the output. The MSB S bits of the output. This MSB S bits is now XORed with the plain text to produce the ciphertext unit. Next phase or the next block, what happens? The contents are given to the shift register, where the contents are shifted towards the left, so that the S bit C1 is placed on the LSB side. The C1 which we have derived right now it places on the LSB side. This process repeats till all the units of your plain text. How many units you have divided your plain text, that much units have been encrypted. This process keeps on repeating. This is just the part of encryption. The equation for this encryption is very simple. As I have already said, for encryption, what is the result which we have, or what's the expected output which we are supposed to get? It's of course a cipher, right? After encryption, what do you get? It's a cipher. Whatever it is, maybe it's as a whole or it's just a part, whatever it is, you receive the cipher in your hand. So I have written C1, let it be for the first unit, is equal to the plain text 1. How did I get the C1? Plain text 1 XOR the SS of encryption K, comma, initialization vector. Because all this time we have been writing encryption of K, comma, X or something like that. So what is the input here? It's the initialization vector for the first one. I have written the equation for this first unit. So that value will be the S bits of that value will be XORed with the S bit P1 to get the corresponding C1. Clear? So this is the encryption process of cipher feedback mode. Now let's see what's happening in the decryption. So now we know what is happening in the encryption process of cipher feedback mode. Now let's see what's happening in the decryption. All this time we have been saying it actually decryption is the reverse of encryption. Here also it is the same, but there's one small difference. Here we don't use any decryption algorithm specifically, because in the decryption process of CFB or the cipher feedback mode, the received ciphertext is actually XORed with the output of the encryption function, okay, so that you get the corresponding plaintext unit. So actually the encryption algorithm itself is needed, or it's actually adequate for this process. Let's see what's happening and how it works. So this is a decryption process. Actually there's a very small modification in your previous diagram. I have just replaced the C1 and P1, that's all. If you can compare, that would be very easy at this time. Here let's see what's happening. You have the initialization vector, the same all the same basic principles. For the first mode, the initialization vector will be the input. So this initialization vector enters the encryption algorithm, which uses the key, some secret keys, k, let it be, and out of this you select the S bits, you discard the B minus S bits, okay. I repeat, S bits is the selected bits out of which or on which we are performing the operation, and the B is nothing but the block size, let it be like B bits, small b. Out of this B, the S bits are being selected, the remaining are discarded, that's all. So the selected S bits are on the left hand side and discarded B minus S bits on the right hand side. Now the selected S bits is actually XORed with the ciphertext which we have in your hand right now. So that is the C1. After the encryption process of the first unit, you have the C1 as the output. That C1 is actually now the input with us, right? Now this C1 S bits is XORed with the selected S bits, which is actually the output of the encryption algorithm, so that you get the corresponding plaintext unit. As simple as that. Clear? I'll repeat it again. For the first block, the initialization vector, it directly enters the encryption algorithm, which uses some secret key, and out of that output you select only the S bits. The remaining bits like B minus S bits are discarded. The S bits are then XORed with the ciphertext which we have right now. The received ciphertext for the first unit is C1. So this C1 is now XORed with the selected S bits to generate the corresponding P1 bits, which is again S bits. Clear? Now let's see very carefully what happens in the second phase or the second unit. In the second unit, this C1 preceding cipher, okay, now enters the shift register. Clear? What happens in the shift register? The bits are shifted towards the left, so that this C1 becomes the LSB S bits. The remaining B minus S bits should come on the MSB part. This is actually the MSB. Now it again becomes the LSB part while performing the shift process or the shift function. So for that you use a shift register. Clear? So using the shift register, now the C1 or the S bits, the preceding cipher, becomes the LSB. Again the process is repeating. It enters the encryption algorithm using the same key k, and out of that result you select the S bits, you discard the remaining bits, and the selected S bits is now XORed with the received ciphertext unit of the second block, that is C2, to get the P2 or the plain text P2 S bits. Okay, so the process is actually simple enough. The main thing we have to keep in mind is that this is not decryption, this is encryption itself, because the output of the encryption XORed with the received CT. CT is ciphertext. After the first block you have C1. Second block, after second block of encryption you have C2. That is the received ciphertext. That is XORed with the output of the encryption algorithm to produce the corresponding plain text unit. Clear? So correspondingly after the second unit you have the P2, and this will repeat till how many units? how many units you have divided the plain text, till that much it will be repeating. So let it be like n-1. The preceding cipher will be entering as the input to the shift register, where the bits are shifted leftwise, and the preceding cipher becomes the LSB S bits and enters the encryption algorithm, out of which the S bits are selected. The remaining B minus S bits are discarded. Now for this S bits selected, the last unit which we have with us, the last ciphertext unit which we have received is the Cn. Let it be Cn. So that Cn will be XORed with the selected S bits to produce the last unit of plain text Pn. Clear? So this is actually what is happening in decryption. Clear? Now let me just say the equation once again. For encryption process, we wrote ciphertext C1 is equal to plain text plus SS of encryption K comma initialization vector. From this equation you can derive as it is. You can just replace, or if you put P1 on the left hand side, what will be the equation? Because after decryption we are supposed to get the plain text, right? So that is the left hand side. P1 is equal to C1 XOR the same. This is encryption itself, not decryption. Clear? So this is cipher feedback mode. What is happening is the block ciphers have been replaced or can be converted to stream cipher, because as long the PT is, that much long the CT will also be. Clear? So in decryption algorithm or decryption process, the output of encryption itself is being used as one of the inputs to get the corresponding result. That's it. Now let's see what's happening in the next mode of operation, which is the last mode, that is counter mode of operation. The last mode of operation that is being performed on the cipher block we have to discuss is the counter mode. As the term suggests, some sort of counter is being set. So what is a counter? You set it like you can perform it in incrementation form or in decrementation form. That is, either you can set it to 5 if the number of units of plain text is 5, and then you can decrement, like by after first block it becomes 4, after the second becomes 3, 5, 4, 3, 2, 1, 0. It can go like that. Or either you can set it like from the beginning 1, and then you can increment till the number of total plain text units, like 1, 2, 3, 4, 5. Initially it's like 1. So that is the basic property of counter, right? A counter is nothing but something like a number. You just take a count just to know which block it is. That's all. So how it works, let's see. So counter mode, it is actually a much more advanced type of mode of operation, and it is mainly used in the commonly used asynchronous transfer mode operation, ATM, for its security, and also for the IP security, internet protocol security. So counter mode is actually, it's nothing but the counter used for this mode of operation is actually equal to the plain text block size. If the plain text block size is 8 bits, the counter is actually, it will go maximum till 8. So initially let it be like 1, and then for the second block it becomes 2, for the third it becomes 3. That is, after the first block onwards, the counter gets incremented by 1, and that's calculated by just like modulo 2 raised to b, where b is the block size. Clear? And make sure there is and very important point, there is no chaining here. Okay, there is no any sort of chaining is not happening here. So what do you mean by chaining? The output of one block becomes in some or the other way becomes the input to the other block. Nothing is happening like that. Each block is different. So it's from that itself it's clear the counter is different for each unit of plain text, and corresponding ciphertext unit is being generated. Clear? The same sequence of counters are used for the decryption process also, and here also you are not using any decryption algorithm, the same encryption only happens. The counter is also the same sequence. Now what differs is, let's see what is happening there. Clear? So moving on to the encryption process of counter mode, you have the counter 1. Okay, first counter you are taking, you are encrypting it. So using some encryption algorithm which uses some key K, you get a encrypted counter, right? That encrypted counter is now XORed with the first unit of your plain text, let it be P1. So P1 XOR the encrypted counter will generate the encrypted C1. That is the first unit of your ciphertext. Clear? Now this is the first block, that is nothing is going from here to the next block. That's what I said, there is no chaining at all. Clear? Now what happens in the second block? You have the counter 2 because it's incremented by 1. So counter 2 is now the input here. It is again encrypted, which is then XORed with the second unit of your plaintext P2 to obtain the corresponding ciphertext unit of your plaintext. That is of course a C2. And this process will continue again and again till how many plaintext units you have, that much times this process will be repeating. Till all the units of your plaintext are encrypted, the process will be repeating. So that much counters will be set. Clear? So let the last counter be n, counter n, which is again encrypted using some key, which is XORed, the result of the encryption algorithm, that is the encrypted counter, that becomes the one of the inputs for XOR function, that is XORed with the plain text available. That is the last plain text unit you have divided, Pn, to obtain the corresponding cipher text unit Cn. Clear? So I have marked a portion in dotted. You can see a rectangle, that is actually the counter mode operation process. Clear? Just to identify easily, I have marked it in dotted box. Clear? So that's all with the encryption. Now let's see what's happening in the decryption process. Just the reverse in the sense I have just replaced cipher and plain text. That's all. Because as we know, after encryption, the thing or the input or the output which we have is actually the scrambled form. You have the original, you gave the original message into the encryption algorithm. Now you have the scrambled form. That scrambled form is a cipher. So now the input is actually the cipher for the decryption algorithm, and from that we are supposed to generate the plain text. Let's see. Here, first counter, the same sequence. How many bits, how many counters you have used in encryption, that many bits or that many counters you are going to use in the decryption also. 4 counters in encryption means 4 counters in decryption also. So for the first counter I'm encrypting it. That result will be XORed with the first ciphertext unit you have generated, that is C1, to generate the corresponding plaintext unit P1. Clear? Yes. That's all with the first block. So there is no chaining, so nothing is being transferred or moved from this to the next block. Okay. In second side or the second unit, what is happening? You have the second counter which is encrypted. That result is XORed with the second unit of cipher C2 to get the second unit of plaintext P2. Clear? This process continues till how many units of plaintext you have been divided, that much it will be repeating. So let it be like n parts. So the last counter will be counter n. This is encrypted. That result is XORed with the last unit of your cipher text you have been generated in the encryption process, that is Cn, and that will be one of the inputs for XOR function. That Cn is XORed with the encrypted counter to produce the corresponding plaintext unit Pn. Clear? So here also a dotted box or rectangle have been specified to note what is happening in the counter mode. Okay, counter mode is actually very easy, but it's very advanced. Okay, it is used for various security purpose. I've already said in IP security, in ATM, in asynchronous transfer mode and all, this counter mode is very important because counter is not repeating. For each block, a counter is there. It's unique. Okay, it's not repeating and all. So the security is being tightened. Clear? So just to conclude, let me just say 2 or 3 advantages of counter mode. This was one question in university question, I guess, in some previous years. One of the advantages is hardware and software efficiency. Of course, it tightens the security. So the efficiency in both hardware and software section is high. Pre-processing is possible. Random access is also possible, and finally the security is good and tightened in a better way. A provable, or you can say identifiable security is being achieved here. Okay, and also as we have learned it in a very easy way or a simple manner, the simplicity of the mechanism, that's a very important advantage. So that's all with the basic cipher block modes of operation we have been dealing. There are mainly 4 modes we have already studied. First one is the electronic code book. Here it's just for a particular key, for a particular plain text or ciphertext is being generated. So as many times the plain text is repeating, the same cipher is being repeating, and you can just imagine a very gigantic book, and so came the term code book. Clear? That's the first one. So to overcome this security deficiency came the second one, cipher block chaining. Okay, and a better version of cipher block chaining is the cipher feedback mode. And the last one which we studied is the counter mode, which is much more advanced than all the 3 else, and that is being used in various security techniques which we use in our current world. That's all.